So this section is on work and kinetic energy. These are connected to forces and Newton's laws that we talked about last time. And I'm going to begin with the concept of work. So we define this quantity called work. The work done by a force is given by work equals the force times the distance, where the distance is how far the object moves while the force is acting on it. Also, in the direction the force is aimed. So if you push a toy car or something like that, let me go to a picture here. Oh, not that picture. That's from the last show. Right? If I have a little toy car here, and I push it with a force F over a distance d, then the work done is equal to the force times the distance. It gets a little trickier if there's a weird angle to the force, like it's this way but the object's moving that way. We won't worry about those. We'll just look at the ones where the force and the distance are sort of either in the same direction or in opposite directions. I'll get to the opposite directions in a little bit. So suppose I exert a force on an object. If the object moves in the direction of the force, positive work is being done on the object. So for example, if I push a toy car, like in the picture, to the right, a distance d, then the work done is the force times the distance. Okay. So let's just look at work for a second. We'll look at the units and dimensions of work, right? And so work is force times distance. Well, if you remember, force is mass times length over time squared, right? Because it was mass times acceleration. And so there's your mass, and you have length over time squared is acceleration. But it's force times distance, so it's another length in there. So the dimensions of work is mass times length squared over time squared. So the SI units then are newtons for force times meters for distance, but the SI unit for a newton we already said is a kilogram meter per second squared, and so the SI unit for work is kilogram meter squared over second squared. That's better known as a joule, or just the letter J. James Prescott Joule was a Scottish physicist who figured out that heat in liquids was related to kinetic energy, was related to energy of motion, which we're going to talk about next. And so the unit of energy in SI units is named after James Prescott Joule. I think he lived from about 18-something to 18-something, maybe 1818 to 1889 or something like that. He lived in the 1800s. So let's do an example here. If a toy car is pushed by a 50 Newton force at a distance of 0.4 meters, then the work done on the toy car by that force is work equals force times distance. So it's 10 newtons. Oh, it should be 50 newtons. Oops. Times 0.4 meters. And so it would be 20 newton meters. Let me pause and fix that. Okay, so there we go. So 50 newtons times 0.4 meters equals 20 newton meters, which is the same thing as 20 joules. So now we can say if the work done is 20 joules, say, and the car moved 0.8 meters, just so a slightly different problem, while the force was acting on it, what was the force acting on the car? In other words, if we reverse the thing and we know what the total work done was and the distance, can we determine the force? It requires that we rearrange this work-force-distance equation to solve for the force, and that gives us force equals work over distance because we divide both sides by distance. That's 20 joules over 0.8 meters. The joules was the work done, and the 0.8 meters was the distance traveled, and that's a force of 25 newtons. So you can kind of work those. You can either start with the work done and the distance and calculate the force, or you can take the force and the distance and calculate the work in those examples. So, so we can also do negative work. So this is a little weird, but let me describe it to you this way. If I exert a force F on an object and the object moves in the opposite direction to which the force is acting, then the force has done negative work on the object. And so the idea here is that, let me go back to my picture, right? Except I'll say, look, now instead of getting the object started rolling and pushing it down the road, I can say, look, my force is, my car is actually traveling along with some velocity v, right? And I want to stop it. So some distance later, right, this distance d, v equals 0. This is like I step on the brakes, right? If you remember, if I'm driving a car, there's a friction force this way when I step on the brakes that brings the car to a stop. And so I can call this V1 and this V2 equals 0, right? The car is brought to a stop. And so the force is acting this way, but the distance is that way. When you get that situation, you use this equation here. The work done is negative the force times the distance, right? So for example, if a car is rolling towards me and I want to stop it, I push it in the opposite direction to which it is moving, and the force brings it to a stop. If I keep pushing it, I can get the car going the other direction. If it's a toy car and it comes towards me, I can slow it down and stop it as it's coming towards me, and then I can start pushing it back in the direction which it came, and then I would be doing positive work again if I was doing that. I should have done this, I think. Hold on a second. Here we go. So let's do another example. Suppose a car is approaching you and you stop it by applying a 5 Newton force for 0.3 meters as it comes to a stop. What is the work you did on the car? So in this case, we know that the work is negative because you're exerting a force opposite to the direction the car is going as you bring it to a stop. By the way, this would be the same thing if you're catching a baseball or a basketball or something like that. As you bring the ball in, you bring it to a stop over a certain distance by applying a force to it. And so in this case, the work done is minus the force times the distance, or minus 5 newtons times 0.3 meters, or minus 1.5 joules. So it turns out you can also have zero work done by a force, and this comes up in a variety of situations, but I'll just talk about a couple of them. In the first example, we have someone just standing still. If I'm standing still here and holding a briefcase up, then I'm applying a force, right? Holding the briefcase up because I'm balancing its weight. But I'm not moving the briefcase at all. And so there's no distance. And so if I were to try to calculate force times distance, work equals force times distance, I would get 0 because the distance moved is 0. And so in the first case, this is one example of zero work done by a force. So this is another one. Another case, if we look on the right, I can say, let me go to the next page. So now what if I'm carrying my briefcase while walking, right? What is the direction of force that I exert on the briefcase? Well, the force is up still, right? I'm still having to hold the briefcase up. It weighs 10 pounds or something. I don't know what it weighs, right? But which way is the distance? The distance is not in the direction of the force, right? The distance is perpendicular to the direction of the force. It is neither in the direction of the force nor opposite the direction of the force. So neither one of the equations we were talking about earlier works. In fact, even though the briefcase is moving, it is moving 0 distance in the direction of the force and 0 distance away from the force. As a result, the work done is still 0. And so you get these two weird circumstances where you might feel like you're doing work holding this briefcase up, but you're not technically doing the physics definition of work on the object. The force, the distance moved by the object in either case is either 0 or 0 in the direction of the force or opposite the force. And so in both of these cases, you get 0 work done. So you can carry a briefcase 10 miles down the road and you've done no work on the briefcase. You might have consumed some energy, but that's a different question. Oh, let's see. Nope. Okay. So now we're going to talk a little about kinetic energy. Kinetic energy is related to work, but first we're just going to introduce it as an independent concept, right? And so the kinetic energy of an object is defined as kinetic energy is equal to 1/2 mv squared, where m is the mass of the object and v is its speed. It should be a lowercase v, but it's fine. So if you know the sprinter Usain Bolt, who's actually been retired for a while now, I think he still holds the world record in the 100-meter sprint. His average speed over that 100 meters is a little faster than 10 meters per second. His speed is over that. His time is under 10 seconds, I think. Like 9.68 seconds or something. If his mass is 70 kilograms, what is his kinetic energy at this speed? Well, again, the definition of kinetic energy, right, is kinetic energy is 1/2 times the mass times the velocity squared. And so that's 1/2 times 70 kilograms times 20 meters per second squared. If you square 20, you get 100. If you multiply that by 70, you get 7,000. If you divide that by 2, you get 3,500 kilogram meters per second squared. But we've already said that kilogram meters per second, meter squared per second squared is just joules, right? And so when Usain Bolt is running down the track at 10 meters per second, he has about 3,500 joules of kinetic energy. So again, this is an important point here. The energy due to motion is called kinetic energy. And this is the formula. For any object that's moving, its kinetic energy is 1/2 mv squared. Let me just do a little side discussion here on this problem. If you notice, if we say the kinetic energy is 1/2 mv squared, right? It goes as the square of the velocity. The v squared, as you know, means 1/2 v times v. Sorry, the v squared means that, but I have to have the m in there. V times v, right? What if, I know he can't possibly do it, it's not physically possible. What if Usain Bolt was doing 20 meters per second instead of 10 meters per second, right? And so instead of, so his speed would be 1/2, his mass is 70 kilograms, and instead of 10 meters per second, we'd have 20 meters per second times 20 meters per second, right? But what is that? That's equal to 1/2 times 70 kilograms times, now follow the magic here. I'm going to do 2 times 10 meters per second, right? Times 2 times 10 meters per second. Because this is the velocity we were originally talking about. I'm just doing some silly math here. And you should recall that you can multiply numbers in any order. So I'm going to pull these 2's out, and I'm going to say this is equal to 2 times 2 times 1/2 times 70 kilograms times 10 meters per second times 10 meters per second, right? This is 2 times 2 is 4. This thing we already evaluated in the problem. This was 3,500 joules, right? So he's doubled his speed, but he's got 4 times as much kinetic energy. That's what that squared does. If he tripled his speed, he would have 9 times as much. I'd have a 3 here and a 3 here. If he was going 5 times as fast, 50 meters per second, I'd have a 5 here and a 5 here. I'd have 25 meters per second. Whatever multiplicative factor I put on the velocity, I have to square that. And so you might think if he was going twice as fast, he'd have twice as much kinetic energy. But he doesn't. He has 4 times as much. This is a really important point in a lot of areas. When you speed things up, the energy they carry, which tells how much work they can do, we'll talk about that in a minute, is determined by, goes as the square of their velocity. The kinetic energy goes as the square of the velocity. And so a small change in velocity, 2 times in the velocity, produces 4 times in the kinetic energy. This is why driving your car fast is so dangerous, because the energy increases more rapidly than the velocity does. And so often if you see an accident report, it'll say the cause of accident was excessive speed. People are not used to it. People don't really understand the fact that it's the energy that's what causes the problem, and the energy goes up rapidly with velocity. Okay, let's come back here and let's talk about how did I do. So now we're going to talk about the relationship between work and kinetic energy. The work done on an object either speeds the object up, like we said earlier, when you're pushing it from behind and it's moving in the direction you're going, or slows it down depending on whether the work is positive or negative, whether the force is acting in the direction of motion or opposite direction of motion. And because it speeds it up or slows it down, it means the work done on an object changes that object's kinetic energy. We just saw earlier that the kinetic energy is 1/2 mv squared. If you're changing v, you're changing the kinetic energy. It turns out the relationship between the work done on an object and its kinetic energy is the work done equals the change in kinetic energy. And so if you do a certain amount of work on an object, you're changing its kinetic energy by the amount of work you did. Since the change in kinetic energy is Ke2 minus Ke1, just final minus initial, it's 1/2 mv2 squared minus 1/2 mv1 squared, where v2 is the final velocity and v1 is the initial. We get the work done is equal to 1/2 mv2 squared minus 1/2 mv1 squared. If the object starts from rest, oops, I'm going to pause this again and fix a quick error. Okay, I think I'm fixed. If the object starts from rest, so its initial velocity v1 equals 0, then we have the work done is just the final kinetic energy. Since the initial kinetic energy was 0, sometimes we just call that 1/2 mv squared, right? V for the final. If the object is instead brought to rest, then we know that v2 is 0, right? Because v2 is the final velocity. And so if it's brought to rest, like the car that was being brought to a stop by its brakes by friction, we know that the work done is equal to 0, 1/2 mv2 squared, which is 0 minus 1/2 mv1 squared, or just minus 1/2 mv1 squared. In other words, if a car was going along with velocity v1, its kinetic energy is 1/2 mv1 squared. In order to bring it to a stop, you have to do minus 1/2 mv1 squared of work on it to bring its kinetic energy to 0. So let's do an example. So a force of 20 newtons acts on a toy car of mass 0.4, that should be kilograms, over a distance of 0.6 meters. The car is initially at rest. What is the work done on the car, right? And so the work done is the force times the distance, which is equal to the 20 newton force times the 0.6 meter distance, which is 20 times 0.6, which is 12 newton meters, or 12 joules. So that's the work done on the car. It's initially at rest. It's pushed with a 20 newton force for 0.6 meters. It gains 12 joules of energy. So the work done on the object equals the kinetic energy gained. This means that the kinetic energy of the object, since it was 0 initially, is now 12 joules. Now we can ask the question, well, how fast is the object going, right? Well, that brings in the relationship between kinetic energy and velocity, right? We know that kinetic energy is 1/2 mv squared. This can be rearranged. I can multiply both sides by 2, and then divide both sides by m, and I get v squared is equal to 2ke, 2 times kinetic energy divided by the mass, and I get v by taking the square root of both sides. Plugging in, we get 2 times the kinetic energy divided by the mass is equal to the velocity. If you calculate that on the calculator, you get about 7.75 meters per second. So a toy car of mass 0.4 kilograms that's pushed by a 20 newton force over 0.6 meters will be traveling 7.75 meters per second and have gained 12 joules of kinetic energy. So final example for work in kinetic energy. A force of 20 newtons acts on a toy car of mass 0.4 kilograms as that car is brought to rest from a speed of 8 meters per second. What is the initial energy of the toy car? So the kinetic energy of the car is just 1/2 mv squared, and that's its initial kinetic energy, 1/2 mv1 squared, right? We know what its final kinetic energy is, right? See if you can do that. while I fix this little typo. So the initial kinetic energy is how fast the car is going when it's coming to you before it's going to be brought to a stop, right? And so its initial kinetic energy is 1/2 mv1 squared. And so we plug in to get, this is 0.4 kilograms for the mass, 8 meters per second. And that's the initial kinetic energy. What's the final kinetic energy? Can you tell me that without looking ahead? So since the final velocity is 0, the final kinetic energy is 0, right? Because kinetic energy is just 1/2 mv squared. And so the work done on the toy car is the change in kinetic energy. It's kinetic energy final minus kinetic energy initial, or 0 minus 1/2 mv1 squared, or minus 12.8 joules. In other words, the work done on the car is minus 12.8 joules. The work took away all the kinetic energy of the car. Right? The car's kinetic energy changed by minus 12.8 joules, and it had 12.8 joules, so its final kinetic energy is 0. Right? What is the distance over which the car is brought to rest? So this gets back to the work, the relationship between work and force and distance. When the distance moved is in the opposite direction of the force, the work is minus the force times the distance. We can rearrange that to solve for the distance. Then we say the distance is equal to minus the work divided by the force, or minus the negative 12.8 joules divided by 20 newtons, or 0.64 meters. In other words, the car moved 0.64 meters while it was coming to a stop, being acted on by this 20 Newton force as it was going from 8 meters per second to 0 meters per second. So a few questions for you to think about. What are the circumstances under which the work done by a force is positive? What are the circumstances under which the work done by a force is negative? Give me some situations where the work done by a force is 0. You should be able to describe the kinetic energy of a moving object, and maybe a little bit about how that depends on the velocity or the mass. Here's just an example. You can say a 0.2 kilogram toy car initially at rest is pushed by a 10 Newton force over a distance of 0.3 meters. You can say, what's the work done on the car? What's the final kinetic energy of the car? What's the, let's just say, final speed of the car? What if you double the distance in the last problem to 0.6 meters? How do each of the numbers, work, kinetic energy, and velocity, change? Is there something surprising about the velocity? So see if you can make those work out.